Okay, so now I'm going to talk even more about diffusion controlled reactions and explain how the rate constant K depends on even more things that you need to take into account. So you have KD, and this is the diffusion controlled rate constant, is equal to 4 pi R star times D times NA. Okay, what are all these symbols? Let's break them down. So KD, again, so this is the diffusion rate constant. And this is really the diffusion controlled rate constant. And so you'll have this 4 pi. So R star is the how close or the distance required between A and B for an actual reaction to occur. So R star equals the distance between A and B for reaction to occur. Okay, so if you're an A, B, B, B. So let's assume that there's some sort of distance between A and B. And so we're going to call this R. And as soon as it gets to like this point and this point, so as soon as A and B are now this distance apart, they're actually going to go through and have a reaction. So R star would be, so it needs to be less than R for reaction to, or sorry, R star needs to be greater than R for the reaction to occur, such that if this is R star and then A and B become closer than that, now they're going to actually have a reaction occur. Okay, so D is the diffusion coefficient. So D equals diffusion coefficient. And what this is this is a quantity that dictates the rate of flux. Let's talk about flux. All right, so if you have a square, you have all of these molecules, the number that go through this square, let's call this an area. So the number of molecules that go through the area per time, then in this area is going to be some sort of squared value. So basically you have like a circle and how many are going to go through per some unit time, that's going to be related to the diffusion. So the flux, we call this J, is equal to minus D times the change in the concentration per change in X. So where this is the number that go through per time, so the number per time is the flux. The diffusion coefficient is going to be the area per second, so m squared per second, and then, or so the number per second, I should say. So the number per second through the area. Actually, I should have omitted the area part there. And then the change in the concentration is going to be how much the concentration changes per distance across some value. So how much the concentration changes across this dx. So how concentration changes across a distance. Sorry, hopefully you can read my handwriting. Okay, so how the concentration changes across the distance, the number of molecules that go through a certain area per second, you multiply those together, and then you're going to get a number per time. So that is the flux of your molecules. So this is known as Fick's first law. I do not know Fick's first name. So Fick's first law. Fick's second law is actually, we're going to get to it in just a little second. But this tells you that the diffusion coefficient is basically the factor that the change in the concentration, or the derivative of the concentration gradient. Let me try that again. The derivative of the concentration, which is called the concentration gradient here, how much that scaled is equal to your flux. All right. So the diffusion coefficient can also be related to some solvent properties. This is known as the Nernst-Einstein equation, or sorry, the Stokes-Einstein equation. So the diffusion coefficient of A diffusing through a material is equal to KT divided by 6 times pi multiplied by what's called eta RA. So KT, so this is KB times T. So there's Boltzmann's constant. 6 pi, this takes into account the volume of the molecule that's diffusing. This is known as the solvent viscosity. And this is the radius of A. So this is called the Stokes-Einstein equation. Such that you can then relate the rate constant Kd is equal to 8 RT over, I think it's 3 eta. When you're incorporating solvent effects. So a note on the Stokes-Einstein equation, you can also relate this to conductivity, the charge migration, whereas diffusion is mass migration. Momentum is called, or viscosity is known as a momentum migration or a momentum transport. These are known as transport properties. And Stokes-Einstein equation, this originates from what's called hydrodynamic theory, where the thicker or the more viscous a material is, the lower its diffusion is going to be. This works for many types of solvents, in particular water-based, which is called hydrodynamic. Water falls under this category. My research actually dives into, pun intended, how this is a poor model. And we're looking at, or I'm looking at ways to, instead of incorporating the viscosity into the diffusion, look at the viscosity as an independent transport property, such that they're not actually dependent on one another. They're two separate parameters that happen to share a same fundamental mechanism. So you may have heard me get on my soapbox about how much I dislike hydrodynamic theory. And here I am teaching hydrodynamic theory. It kind of makes me twitch a little bit. But again, the Stokes-Einstein equation, it works for many systems. For many systems, it does not. And that's where the edge of our ignorance really helps push us forward. Or we find the edge of our ignorance when it's like, okay, when we try and apply this model to systems and it fails sometimes, the data don't match. You don't get an inverse relationship between diffusion and viscosity, especially on materials like ionic liquids that are all charged ions. So more research to be done. More research to be done indeed. Okay, so there's hydrodynamic theory. I taught it. There's the equation. Moving on. All right, let's talk about the mass balance equation. Dealing with the flux. So, or the material balance equation. So we have the change in the concentration per time. That is equal to, and I'm just going to give this to you and then explain what it means. D times partial derivative of J partial T squared. Sorry, this should be an X squared minus V partial J partial X minus KRJ. Okay, this is known as the material balance equation. And really what you need to think about this is as you have a material moving, as you have liquids interacting with each other. So on a molecular level, the number of collisions is very limited. You've got such a high density that the odds that you get the right molecule and the right molecule together are going to affect the reaction. How many you have, the potential energy surfaces around. So many things dictate how J is changing with time. And also, if J changes with time, it might react into something else, therefore changing the concentration gradient, which would then change the diffusion, which would then change the interaction rate. So what the material balance helps us do is helps quantify bookkeeping for how these materials are changing as they're flowing. Cool. Okay. So this is the amount of J entering a region. Awesome. Okay. This is Notice it's a negative sign. We're losing some J depending on convection. This is velocity due to convection. And so this is a loss. So this is a loss of J due to thermal convection. So not only do you have, if you have a reaction, and then here you have the loss of J per a reaction occurring. Notice how you have this Kr here. So as you go through each of these different quantities, if you have a certain box and you have, okay, a certain number of molecules in it, J's, right? And some of them are going to diffuse out such that they're not present in that little area to then quantify how many can react. Or you might have, so that's how many you start with. Or so then you might lose some of reaction due to the fact that there's going to be a natural flow, or there's going to be a spontaneous flow due to convection effects. Heat rises, that thermal energy is going to make itself move. And so you're going to lose some J that can then react. You're also going to lose some J based on the fact that J has reacted into something else. So A has become B. And so to quantify where the molecules are, it's not just that when you're quantifying a solution that you have A and B react become C. It's going to be that you have to take into account now all of the different qualities of a liquid while reactions can occur. So lots of things to keep track of. Let's see. So this is the material balance equation. Notice that this is also a second order differential equation because we have the second derivative of J, and I should also say this is known as Fick's second law of diffusion when these two are zero. So you can basically say that when you don't have convection effects and you don't have any reaction, that all goes away. This becomes Fick's second law. But you can solve this differential equation to find J as a function of time, which remember, at the beginning of kinetics, I told you that we were going to go through various avenues to find concentrations as a function of time. Well, this is kind of like taking into account everything of not just reactions, but also the dynamics of the fluids or dynamics of the molecules in the liquid phase. So the answer to this differential equation is equal to, here we go, N0 e to the minus x squared over 4 dt divided by quantity A times pi dt 1/2. Okay. Oops, that's not a 4, that's an A, my bad. Yeah. Okay, so this is an area. A is an area. N0 is the initial number of molecules across that area. What else? X is just that distance x per some amount of space. D is the diffusion, D and D, that's the diffusion coefficient, and then there's your time. Cool. Okay. So why do we care about having this? Well, we want to be able to relate what the quantity of J is at any given time, and this helps us then normalize how many molecules we have per certain area, but then also how many are being affected by the diffusion, by the convection, as well as by the reactions that are occurring. So this gives us a snapshot that is out of equilibrium. That's the other thing. Most of the experiments that you've done have been equilibrium experiments when you're determining the concentration of something. This is a time-dependent concentration because you've got chemistry going on as well as physics with the diffusion. So how do you take it into account? That's one way. Go team. Okay, I think that's all on mass balance and diffusion controlled reactions and such. Yay.